Welcome back. Hope you are eager to learn another new machine learning algorithm. In this session, we'll be talking about SVM or support vector machines. SVM allows us not only to solve linear problems but also to solve nonlinear problems. The idea behind SVM is the algorithm creates a line or an hyperplane which separates the dataset into classes. So essentially, given our entire dataset, we'll be able to draw a particular line which will be bifurcating our dataset into two classes, where each class is homogeneous as an assumption. So in theory, we input our data into our SVM, and as an output, we get the equation of a line which separates our dataset into a distinct classes. Let's take a look into this diagram that is coming up on the screen. Our objective over here is to separate the red squares from the blue dots. Now you might think that that's an easy way to do it, right? We can clearly draw a line in the space in between. But take a moment to think, what would be the best possible line to separate this? Would it be the yellow line or the green line that comes up? And that's the catch. That is where we need to understand which is the best suited line for a given data set. And this is actually calculated by our SVM algorithm. How does it do that? So the first thing is, given a plane or a hyperplane, we try to find a point in the class which is closest to this hyperplane, and we call this, for that particular class, a support vector. Similarly, we calculate the support vector for the other class, that is the point which is closest to the line separating this or the optimized hyperplane. And the distance between these support vectors are called the margin. And this is where the optimization starts. We need to find such plane which maximizes this margin. And once we have maximized the margin between the various support vectors, we get the optimized hyperplane or line which is able to divide our data set into two classes. Now this was a very simple example where we could get a line which separates the dataset into two different parts. Let us take a look into a little more complex dataset. Let's take a look into this dataset which is coming up on your screen. As you can see, this is not a linear problem, and more importantly, we cannot develop a linear line which divides the entire datasets into distinct classes. How do we approach this problem? We do this by transforming the data to a higher dimension. So we insert another dimension to this problem which we call as z, and this z is equal to the sum of the squares of x and y. So z equals to x square plus y square. When we do this and plot the values, we can see that now this previously non-linear looking dataset transforms into a dataset which can be separated by a line. And this line, let's call it k, would be equal to x square plus y square. Now let's go back to the previous dimension that we had come from. Now how would that particular line k look like over here in this lower dimension? This line k, which is equal to x square plus y square, looks like a circle in the lower dimension. And as you can see on the screen, this particular line, or rather circle, is able to divide a class into two distinct classes, and this is what we had tried to achieve. So by increasing the dimension of the data, we are able to find a linear line which can divide the class into multiple classes in the higher dimension, and that's representation in the lower dimension can be again assessed from the equation of the line from the higher dimension. This is how support vector machines work. And more importantly, there are two parameters that we must keep in mind when we are developing SVM. The first parameter is called the C. It is basically a trade-off between the smoothness of the decision boundary that we are building and the exactness of the boundary in dividing the classes. That is to say, if the value of C is very large, then our decision boundary will exactly fit and classify the dataset into distinct datasets. But in doing so, the line won't be very simple. As you can see, the line tends to be very curvy, and there is a high chance of overfitting our dataset. And for a C value which is very high, we would be getting a straight line which may not be very accurate in classifying our data, but it is a much more generalized solution. So with that, we would come to the second parameter that we must keep in mind, and that is known as gamma. Gamma is actually the influence that a particular point has on the decision boundary that is being generated. So if the value of gamma is very low, we will be coming up with generalized solution, because even furthest away point would have a significant impact on the decision boundary that is being created. But if the value of gamma is very high, then points which are closer to the decision boundary would have much more influence on the nature of the decision boundary, and hence a decision boundary would form much more of a curvilinear structure and it won't be very generalized. So we need to find optimum value of gamma along with the optimum value of C to find a model which best suits our needs. Let's look into some of the application now of this particular algorithm of SVM. SVM is very much used to detect facial expressions and recognitions. So essentially, given our data set where we have multiple facial data, we try to understand a decision boundary which can classify these facial expressions. For example, we need to find which facial expressions are an indication of happiness and which facial expressions are an indication of sadness. This particular SVM algorithm is efficient in developing a decision boundary which can classify our image data into such distinct groups. Another application of SVM is for text analyzation. So in text analyzing, what we can do is we can have handwritten data which we want to convert to computer text data. Similarly, over here we have a lot of handwritten data which can be labeled into the computer data, and we can then create certain decision boundaries which gives us an understanding of what handwritten symbol represent what computer text in our data set. And another important area of application of SVM is to analyze geospatial data. Now let's take a quick example of how this can be used. Suppose you have two franchisees and they are located close to each other, and now we want to understand which of the customers will be catered by franchisee 1 and which would be catered by franchisee 2. So to do that, we again take our geospatial data and develop the decision boundary. And on either side of the decision boundary, we'll have our two franchisees, and each franchisee would be catering to the population which is on their side of the decision boundary. This is another quick and good example of how SVM is being used to solve business problems. Hope this session was interesting and hope you had fun, and hope you learned how SVM can be used to classify our data and understood where its true applications lie. Thank you. Hope to see you in the next session again.